Tutorial 9, question 1. Let us focus on these sub-questions. C and E. Let me switch the screen. This is the program. As you can see, we want to print out as you can see, after the user enter the input text, the program will print it out over here. The first one, for question C, 1C, we are going to print out, the input is percentage %D. So we are going to execute printf %D. In question E, we are going to printf %S. Okay. Let's see what happens when we execute these two input with these two different input. First, compile the programs. This is a warning message. Okay. That means that the program is syntactically correct, still can be compiled and can be executed. First one, %D. If we instead of printing out %D, okay, the integer value 73896 is being printed out. What about this? Okay. So instead of printing out the %S, a segmentation fault is occurred. So to understand why these two are different, why the behavior is different on these two inputs, we have to know two concepts. First one is the call stack, and second is the string representation in C. Okay, let's look at call stack. When during runtime, when the function is invoked, the runtime environment will create the local environment of that functions and put it into a stack, which is called call stack. So let's look at what happens if we invoke this function. When this function is called, during runtime, an environment for this printf, a local environment for this printf is being created. And what does this local environment consist of? First, it consists of a very important thing is a return address. Okay, and so a return address, put it here. And second thing is the arguments, the parameter to be passed to this the printf. In this case, it's %D. There's only one argument. Okay, so we need to put in first argument, okay, or first parameter and second parameters. So that's what the third group of things, information to be stored are the local variables. Okay, in the printf, the function that consists of many local variables, and those local variables will be stored somewhere here. So there's a three main portion. First portion is the argument, the parameters. Second portion is the local variables, and the third one is the return address. That means that when this function is completed, where should we go back to? The actual representation of this information, how this information is represented, differ in different compiler and OS. This piece of information, as mentioned in the last lectures, will be pushed into a stack, and we call that stack the call stack. So now, okay, when printf is evoked, okay, this environment is formed, okay, and there's one part that store the first argument. So first the percentage D, this string is stored around here, somewhere for the first argument. There isn't a second argument here. Okay? So when there's no second argument, all the rest of the information will be pushed out. For example, the return address will come out, or some local variable will come out. They depend on representations. So when printf is invoked, after this thing is stored, constructed, pushed in the call stack, the control will go to the printf main bodies. The printf, the logic of printf will scan through the first parameters. First argument will go to extract out the first argument, and then one by one, character by character, print it out on the screen. When the control hit a percentage D, this is some control constant, okay, identifier. When the logic of the printf, when they hit a control D, it will go to search for the second parameter, second argument, and print it out as integers. So in this case, there's no second parameters, okay, but the logic of the printf will still go to the supposedly location of the second parameters, which is somewhere here, and pick the value here and print it out as integers. Okay? Because printf in this particular instance, there's no second parameters. Information stored here will be some others, for example, other local variables, or even the return address, depending on implementation of the compiler. And thus, in this case, just now as we see in how we run this, okay, something is printed out, will be 773 over here, okay, 73896. So 73896. Okay, so what is this 73896? At this point of time, we do not know. It could be a return address or some local variable. Okay. So now let's look at another instance. What if instead of percentage D, percentage S is put in, and we will get a segmentation fault. Okay. Why this is different from first one? Likewise, when the printf is invoked, printf percentage D S, this part is for the argument, for the parameters, this part for local variable, and then return. There's only one argument, one parameters, so percentage S is here. Same as before, when the control flow go to the main program of the printf, and printf logic will scan through here and started to print a character here. When you hit the identifier of percentage S, you will look for the second parameter and treat it as a string, and print it out. So you come over here, okay, and treat this part as a string, and print it out. Now we have to know how C program represents string. Okay. In C programs, the string, they use the null termination representation for string, and suppose the string HELLO. Okay, the end of the string, as we mentioned quite a few times, is implicitly indicated by the value, the null characters, which is the value 0. Each of them is 1 byte. This is an array. This is array. And this is the starting location of the array. Okay, let's suppose that this location is memory location 1020. In the string representations, when a parameter is, let's say a variable s is a variable, let's call it t, is a string. It doesn't explicitly store the HELLO, the whole array. In C representation, t actually is the pointer to the starting point of the string. And in this case, if t is of a string type, the value of t is 10020. Okay, so that you can imagine this a memory location. This part is to store the string t. Okay, and it's not the whole array stored here. It's, instead of the whole array being stored here, is the pointer. The address of the starting point of the array is stored here. So now, get back to printf during runtime. When printf is invoked and the control go to the main program of the printf, you started to scan this, and then he will search for the next parameters, happen to be this location, and treat this part as a string. Remember that in the C representation, this is actually a pointer pointing to the starting address of a string. So what is this value? Just now we know roughly this one is 73896. Okay, 78396. So at 73896, so this is a location of 78396. So there will be some value here, some character here. So printf will now go to 78396 and started to print out all these characters. You keep doing so until you hit the percentage, the null characters. However, okay, but what we can see here is that it's not a string being printed out, rather than a segmentation fault is being printed out. Okay. The main reason is that memory located for this address, okay, is limited, and there are certain part of the memory this process doesn't have access to. Okay, so if a process attempt to access location that he doesn't have access to, or is going out or about, then a segmentation fault will be raised. A sectional segmentation fault will be raised by the OS. Okay, these processes request, the printf request to access these memory locations. If this memory location is not available, okay, because out of bound, or the process doesn't have access right to, the OS will prevent it. The OS, there's a, I call it, I draw it as a policeman, right? So we got a reference monitor will then deny access and raise an exception, and this exception is segmentation fault. Okay. So in this particular instance, 78396 is probably out of bound.
Question 2. Question 2 is also about the call stack. In question 1 is about the parameters, the argument. Question 2 is on the local variable. This is the program of question 2. Over here, there are few local parameters. As you can see from here, the local parameter, we have A, T, and B. When this main program is invoked, the local environment of main is created and pushed into the stack. So, as mentioned in the question 1, two important pieces of information is the return address, which I'm not going to touch here, and there is question 1 focused more on the parameters. And this part is the local variables. And in the core stack, some portion will be reserved for the local variable A and local variable B and the array T. T consists of 5 elements. Okay. First part is rather not important. It just says that text is actually equal to T. Okay. T is a pointer pointing to the beginning of the array. And now it started to string copy, and copy into T. So there's a 5 element, 1, 2, 3, 4, 5. Okay. And then, okay, so let's try to run the programs and see what's happened. So let's compile the program. Q. One, two, three, four. Okay, so the string 1, 2, 3, 4 is copied into the text, and then the printf function is called to print out the 1, 2, 3, 4. So what if we put in 1, 2, 3, 4, 5? 1, 2, 3, 4, 5. Okay, this is being printed out. Okay. So what's happened is this. In the first case, when we put in 1, 2, 3, 4, we copy 1, 2, 3, 4 over 1, 2, 3, 4. And the null character is copied over. So this is here. So next, if we want to print out T as a string, so it will be print out this null termination. It will be print out 1, 2, 3, 4, now stop. So that's why we have 1, 2, 3, 4. What if we copy in 1, 2, 3, 4, 5? Okay, if we call in 1, 2, 3, 4, 5, so instead of a null character there, 5 will be put here, and the null character will be copied over also. The null character, in fact, will be overflow to the next part of the stack. In this case, is putting over here. You look at the program, the last before the printing. So now if you look at the program, let me switch the screen. Let me switch the screen to the questions. Okay, look at the questions. So then 1, 2, 3, 4, 5 is being copied over, and then the null character is overflow to the A, and then when you print out, and we'll print out 1, 2, 3, 4, 5. Let me draw it here. So this is a core stack. This is a portion for the local variable, and this part for the variable, the array T. There are 5 of them being reserved. Okay. And this part is to be stored A, and this part is T, this part is B. So this starting 1, 2, 3, 4, 5. When the string copy, you copy 1, 2, 3, 4, 5 plus the null character. Okay. Now if you want to print, the string is starting from text. Text actually point to the same location. You print out 1, 2, 3, 4, 5. Saw the null character and stop. So hence we print out 1, 2, 3, 4, 5. And next line actually override return this part with the character A. So when the printf attempt to print out the text, print out text also pointed to here, we'll print out 1, 2, 3, 4, 5, followed by A and something that we do not know what it is. You keep doing so until it hit a null character 0. Let me switch back to the screen. Okay, so as you can see from here, the first one is print out 1, 2, 3, 4, 5 as we have just expected. And the next one will print out 1, 2, 3, 4, 5, A, followed by some number that we do not know what it is, and it stopped here because it happened to be 0. If it's not 0 here, you keep on printing so, and to the end. So you can try to run it again, and okay, sometimes it will get an inconsistent result. Like here. Over here is colon, and then it's a question mark. Okay. You wonder what's the meaning of question mark. Question mark means that this is not ASCII character. Okay. So let's go to a question 3. Question 3. Okay, question 3 is on Unix command. Let's skip that. And we go for question 4. I've got the answer. Let me switch the screen. Okay, question 3 is a Unix command. Okay. Question 4, you can just refer to the solution I post. Question 5. Question 5. Question 5 is a very simple program. In this program, we declare an array of 10,000 characters, and then one by one, you print out the characters. Okay, what would be the output? Okay, we declare a characters, an array, 10,000 of them. And what is the initial value? Should we print out as all zeros? Let's switch the screen. So question 5. Question 5. It is question 5. And this. Let's see. This question 5. Okay, over here we have question 4. So I will start to run this, compile these programs. Question 4.c. This is actually question 5. Okay, question 5. Let's start to run question 5. Okay, we see a branch thing. It's not all 0. It's supposed to be 0. This because the C program there's no initializations. Okay, when you declare an array, there is the compiler did not generate a program that initialize the array. So you will just print out whatever in the memory. So one interesting is this: if you try long enough, okay, it just happens that it doesn't appear in my current instance. Is that in some cases, there are meaningful value here. Okay. Even recognize readable ASCII characters. Okay. So what the implication is this: when you started to print out, you have a lot of data, and this data possibly could be sensitive. It's not what you want the user to see. But if you initialize when we declare an array and we did not initialize to 0, potentially the person who run the program may be able to get some information. Okay, So over here like this, you see there's some meaningful name over here. Okay. So this may cause some privacy compromise of confidentiality. Let's go to the next questions. Question 6. Question 6. Okay, this is question 6. Okay, I think I named it wrongly. Question 6. Okay. So basically, there's two conditions here. Okay. No, because a value of a is 40. So normally, the total is to add with a string length of a string. String length of a string is always non-negative. So we expect that the total cannot be less than 40. So then this part say that if total less than 40, this is what attacker want to see. And if total more than 40, this is what attacker doesn't want to see this. Okay. This will be a normal circumstances, but the attacker want to enter a string so as force this condition to appear. Okay, look at the logic. We assume the attacker can control the string to be entered. And you want to enter a string so as to force this condition to appear. If you follow the logic of this, you found that it's not possible in some sense because a is equal to 40 and the length of a string cannot be negative. So total can never be smaller than 40. Let's run the programs. Q6. Sorry. Q6. One more warning message. Q6. Enter your name 8888. The attacker want to see this. Okay. And this is a normal usage. Let's try a longer string. Still don't want to see this. Fortunately, I prepared the string. This is the string. Okay, so you print out this. This is what the attacker wants to see. Some Unix command. Okay, if some of you may know that I can do this because this file A store this a string of zeros, and I can catch a 6. Okay, it is get what I want, and also can do this. So what's happening is this. Okay, let's look at the program, and I will switch screen. This, as explained in the lecture notes, okay, total is unsigned characters. That means it's 8 bits. And when we try to add these two together, string length, so because total is 8 bit, this addition Okay, implicitly, actually, it means total equal to A plus this string something modulo 256. So if we want to force this to be total to be smaller than 40, we just have to get this part, for example, equal to 256. This part equal to 256, total will be 0. So how do I make it to 256? We know that A is 40. So if str is a string of length 226, we add up, total will be 0. Okay. So this is what happened just now. The number of 0 that I key in is of the length around 226. Okay. And such is, in fact, it's exactly 226. Okay, then the total, that's why we force this condition to appear and print out this line. Okay, with that, end the tutorial.